I'm going to introduce Dr. Manuel D'Abreu. He's the co-founder, senior VP, and chief scientist at SmartIOPS, and developer of very high-performance NVMe SSDs and appliances. At SmartIOPS, he drives the technology roadmap, development of new products, and innovation. But before co-founding SmartIOPS, he was a fellow at SanDisk, and he worked on error correction codes, flash technology and reliability, and managed efforts in NAND, SSDs, controllers, and test. Well, he has 35 years of experience in the semiconductor industry, and his expertise spans system on chip, or SoC, system and package design, test and manufacturing, signal processing, flash storage, and coding theory. Before all that, his work experience included living in upstate New York in Schenectady and working at GE Research, working at Honeywell in Phoenix and Minneapolis, Intel for a very long time, and then SanDisk, as we mentioned. So he really has a very extensive experience. He's also an active member of the professional high technology community, and he's been an advisor to the National Science Foundation and an adjunct professor at Santa Clara University, which is really close to here. He's an IEEE Life Fellow, and his work has been published in or presented at more than 50 technical conferences and journals. He's been granted more than 80 patents, many more pending. And he holds a PhD from the University of Texas at Austin, or UT. And it's my pleasure to introduce Dr. Abreu. Thank you.
Oh, thank you, Roberta. Okay, thank you, Roberta. Now, I'd like to, first of all, I'm going to give you an overview of what SmartIOPS is all about, and then tell you a little more about our products and what our next generation roadmap and what is coming down the line. Okay, now, storage providers, they all have a holy grail. And of course, the holy grail has to start with the scroll. The best, everybody wants to get the best performance per dollar. And the way to do it is by providing a higher IOPS. And the best price for storage. What is interesting is that when I say best price per storage, the storage providers do not control the price of the NAND. So only thing they control is the multipliers, how much they can charge to the customer for a gigabyte in storage for an SSD. And of course, we try and charge as much as possible because our most important goal is to make money. But the real challenges, that most providers really overlook, need to be addressed. And I'll talk about that. Now, when we talk about performance, there's more to performance than just getting more IOPS. It's the quality of performance. The first generation SSD, the major focus was on providing pure IOPS, increase the number of IOPS you can get. And that was fine because you were comparing against the HDDs. Now, but the customers really, when they want IOPS and they're paying for it, they really need to know what benefits they are getting for the increase in performance. And that's very important. And everything has to be related to the performance, to how you can gain in your application, improvement of your application performance. Now, what next generation SSDs must deliver is quantifiable gains. And this relates to an application. So if I have a database that typically runs for about 10 hours, and if I can run it, accelerate it, and I have it run for 2 hours, then I can quantify my gains. That's very important. Not only IOPS, but quality of performance. And later on in the presentation, I'll describe that and I'll tell you what we mean by quality of performance. Predictable performance at different workloads. That means a lot of times we've seen people that say, oh, we can do 1 million IOPS, but they'll do 1 million IOPS under optimal conditions. We believe that when you say that you're delivering some performance, it has to be across different workloads. And I'll give you some data and I'll show you what has been achieved. And something that's extremely important is a value added. Your SSD has to be more than just a storage device. You have to build intelligence into it. And I'll I'll talk about that in detail. Most of the presentation will be on how to make SSDs intelligent and what we have accomplished. And what's important is that addressing all these requirements really requires a lot of innovation. You just cannot take a standard storage architecture and trying to deliver everything that we are promising. So to set the baseline, let me talk about what are the enterprise SSD, what are the 5 characteristics. Number 1, predictable high read performance. So if I'm going to say this thing runs at 1.5 or 1.5 million IOPS, it's got to be predictable across all the workloads. Number 2, random write performance. If I'm saying that my performance is 500K, 600K, it has to be predictable. So I can't see big variations in that. Number 3, latency for read and write and across different workmates. This is very important because there are a lot of customers where latency is key, and we have to be able to satisfy them. And quality in terms of RAS, where RAS means reliability, availability, and serviceability. We have to be able to make sure that the data is available, the SSD will last, and the quality of service will be good. And the last one is features. We need to have features to accelerate applications like security, databases, protocol, and so forth. So with that, let me introduce one of our products, which we call the Data Engine T2 and high performance. HP stands for high performance. Not yellow packet, it's high performance. Okay, highest random reads. If you go across the floor, you'll see that nobody can come up to what we have. We have 1.7 million random read IOPS. Only one in the market, nobody, and we'll stand behind that claim. Highest random writes, right now, and by the way, if you go to our booth, you'll see a lot of this data, and this has been validated by an external company. We didn't generate the data. Some external companies like Aerospike, and they have actually tested our drives, and they came back with the data. Right now, we are at about 600K, but in the lab, we have drives that run at close to about 1 million writes, random writes, and we'll be releasing those products sometime soon. Low latency. Okay. Really, very specialized heuristics. We have some very nice heuristics to help us reduce the latency, and this is important for applications like database, AI, and so forth. Okay, enterprise quality. We must sustain performance. It's very important that performance doesn't degrade over time. We have power loss protection, adaptive techniques to be able to increase endurance and increase and maintain performance. And we have a lot of fault tolerance techniques and algorithms implemented in our drive. Very feature rich. It's NVMe 1.2 compliant. SROV, very large namespace. We provide features like for dedupe inside the drive, for data shaping, open channel support, and so forth. Now, and the thing I highlighted in blue really is what distinguishes us from everybody else. And this translates really in 4 to 5 times the performance. Now, SSD, you cannot come up with one SSD to meet all the requirements. So what we did, we broke it up the market segments. We have a low, very well-balanced, high-performance and low-latency SSD. Then we follow that with a very low latency, and this is really unique. It rivals the storage class memories at 5 nines of latency. We are really very, very efficient, very good. And when I say a 5 nines latency of it's about 200 microseconds, that's using 3D TLC. It's not SLC, but TLC. And with that, it's very difficult to get the latency that we have achieved. High capacity provides capacity for, and high bandwidth without loss of performance. We can give you very high performance and high capacity. And this, actually, we have a drive which has about 25.6 terabytes for usable capacity for the user. Now, how did we come up with all these market segments? How do you do that? We actually worked with a very known agency to try and figure out which is the biggest consumers of storage and how we can work with them. So we worked with NSA. So NSA is very familiar with where the data resides and who's got the data. If you look at this, porn really has the highest capacity, needs for the highest capacity in storage. So You need to be able to provide that for them. Performance, social media, everybody wants to perform social media. Terrorist activity, low latency is very key. Now, I just want to let you know that we haven't forgotten spam. Spam is very important. So we have smart storage to help us identify spam and reduce the amount of spam. Okay, so what about performance? What type of performance do we deliver? For our high performance drive, the read operations is 1.7K, it says 1.7 million IOPS. The latency is 208 microseconds. You see the 2 nines latency, and the 5 nines is 1 millisecond, and that's a key thing. And our low latency product, which again is a 3D TLC product, is 800K performance. We had to make some sacrifice. You lose some performance, but you gain in latency. You reduce the latency. Average latency is 104 microseconds, 129, 2 nines is 129, and the 5 nines, 250. That number, the 250 microseconds at 5 nines, is really amazing. And we did all this, all raw performance. There's no compression, no tricks. And performance that we achieved across all drives. When I talk about SmartIOPS, our performance is 1.7, it's predictable. The performance, if you see our demo, you see it's pretty much a straight line. You don't see a lot of variation like you'll see with some of the drives, competitor drives that I show on the left side of the screen. Key value database bench results. This was not done by us. This was done by a third party. They took our driver and evaluated this. Okay, this was done by Aerospike, and they published this data recently. And of course, by the way, I just wanted to mention that our data drive that we evaluated here is at about 600 transactions per second, but we have a drive in the engineering sample that goes way over that. That tells you we're about 3 or 4 times, 3 times closest, faster than the closest competitor. Okay. And what is unique, our latency, again, is really within the 1 millisecond latency. It's within 2, very, very rarely it goes above 2%. So it's predictable latency. And that the data speaks for itself. You can see what the other drives do. This is an interesting example. We took the data and that showed the test setup. It was a standard, the data published by one of our competitors. We took the same thing and we ran it. This is a database, a Cassandra Yahoo Cloud Systems benchmark. And what is interesting is that our competitor took them 6 hours to complete the task, and we did it in 2 hours. So 3x performance, and that's a value. So that can be translated into dollars. Other benchmark that we have done is using Orion, I/O numbers. This is where other people on normal SSDs generate, and this is where we are, our performance. So this is a standard test that we run, and as you can see, our performance is much higher, and our latency is much lower than anybody else. And latency comparison at performance. When you measure latency, don't do it when you have a QDAPT of 1. You have to do it under real performance, under real application, when you run some real applications. And that's where you see, and that's how we distinguish ourselves from anybody else. If you see most of the people, they'll give you latency for single access, but then you got to test it when you, on the performance, on the run large applications, and that's where you see that we really shine. Power efficiency, these are some of our competitors that you see, and this is where we are in terms of IOPS per watt. And I'd say we are really the highest IOPS per watt in the industry. Nobody comes close to us. Now, one thing I like to do is introducing you to the next part of my talk, which is, again, in storage computing. Now, general purpose computing, something that Intel came up with general purpose processors, then graphics computing, NVIDIA, and they are the leaders. network computing, Cisco. And I'd like to mention that we came up with what we call storage computing, SmartIOPS, and we'll be the leaders in that. So what is storage computing? Really, computing on a very large data set, which does not fit in a DRAM cache and needs high-performance storage I/O access. Basically, you have the data on your non-volatile memory, and you need to be able to access it very fast and process it very fast. And applications, will be like databases where you sort, join, searches, genomic sequence, machine learning, native file system support, like open object store and data dedupe. Okay. Now with that, let me tell you what our accelerator, what our storage computing looks like. This is a generic view of an internal view of a controller. Has your array stack, storage complex has your array stack, which is all the NANDs, has a controller. Like specified, we built our own controller. It's based on true random technology, which is something that we have a trade secret, and it's a registered trademark. And internally, this SSD that we have works at over 2 million IOPS. The problem is that the PCIe is a bottleneck, so externally we can transmit only 1.7 million IOPS. So what do you do with the extra capacity, extra speed that you have internal to the drive? So what we do, we provide what we call an acceleration complex. That's where we can put a lot of algorithms that need to be accelerated, and he's connected very, very high speed link to the controller and talks directly to the memory. So if you have algorithms that run, so the acceleration controller can talk directly to the memory. And of course, we have a library of applications that can be downloaded dynamically in real time, and it can be changed as an application needs and so forth. So we have what we call really an application acceleration engine, and we call it TX-AX, for AX stands for application acceleration. Of course, the user has at his disposal a library of algorithms that we worked jointly with some key customers to develop, and they have access to those libraries. But the user also has an environment where he can develop his own libraries. If he has special sort techniques or special search techniques, you should be able to develop those algorithms, put them in the library, and then he has access to them. Now let's see what the implication of this is really in a virtual environment. The physical view of a virtual environment, you have your server, and the server talks to the storage system. And the storage that I have in there has where some algorithms have been preloaded. But remember, these algorithms can be changed in real time. In the virtual view, you have multiple users that need to be able to access. And every user, they'll have their own access and their own algorithm. Or, we can have multiple cards with different types of algorithms and that the users can use this. This is a tremendous benefit for in a virtual environment. For people that need a virtualization, they get acceleration. And the fact that we have very high performance between the host and the storage, the bandwidth is very high. So now the average latency, the average efficiency of the virtual system goes up. If you're limited, if you have a server that has very high performance, but if your storage I/O is very low, then the efficiency of your system is overall is very low. But if your efficiency of a host is here and you increase, if you raise the efficiency of your I/O, then the overall system efficiency is much higher. And we can do that. So what is unique, as you can see the arrows show there, every virtual user can access all the different types of algorithms which are downloaded there. Algorithms can be changed in real time. So if there's a request for different types of algorithms that need to be loaded, if the algorithms are in the library, they can be loaded, or the user can create his own library, add to the library. So availability of very high performance SSD is very important to relieve the storage I/O bottleneck. And we've accomplished that. We can do that. So we have to enable users to access accelerators. So the accelerators, again, like me to rate, reside in a library and can be swapped as needed, and it can be swapped in real time. And there's an infrastructure to enable the user to develop new algorithms and verify and incorporate them in the library. And in a virtual system, we can support multiple algorithms concurrently, real-time customization of the storage, and algorithms can be changed. One thing I like to do, if somebody asks me a question, how can we do that? Our accelerator engine is programmable. Right now, it can be an FPGA. It can be a special processor. And we are working in what we call a neural processor, which is an extremely high-performance neural IC that will go there and enable a lot of these algorithms. So sample the algorithms. For example, for gene sequencing, you have your nucleus, you have your chromosomes, and you're trying to sequence them and get the DNA. You're dealing with tremendous amount of data, and it requires a lot of searches and a lot of computation. So the DNA sequencing really means find the complete ACGT sequence in your DNA. That means it requires a lot of searching, a lot of I/O. So to sequence all DNA base pairs, in the human genome, and to find the 20,000 to 250,000 human genes is a very complex problem. You have to find many mappings for each read. So you have multiple reads, and some of the mappings will fail, but you need to be able to do that. So the human DNA is really about 3.2 base pair long, which is very long, and millions to billions of reads. You do lots of reads, so it means it's read intensive, and then you need a lot of searching and a lot of compare. And the read algorithms typically used are either hash-based or BW transformers. And to do the mapping, the bottleneck, that's where the thing falls apart. Really to go from 300 million base pairs to because there's no acceleration, there's no way to do it, the current way, the efficiency drops down to about 2 million base pairs. That means it's about 150x slower. So there's tremendous room for improvement. So that's why we come with our hardware acceleration. Near perfect hash techniques. That's what we have implemented. It's over 100 million searches available. Shift, compare, logical operation performed at hardware speeds, and very high read and write times. This is extremely important when you do the read. And this, we implemented this in our engineering sample just to find out using what it would take, and the inherent parallelism that we have right now gives us a 20x gain. But this is just the beginning. We can get much, much higher performance, a lot more gain as we work with some of the key customers. We have some joint development, we'll work with them, and that'll help us to speed this thing up even more. Other accelerators, we have for data deduplication, we have about 27 million 4 KB matches in real time. And database algorithms, I'll show you some performance that we have on database algorithms. Okay, database performance versus latency. This, again, highest performance at lowest latency. And this is because of this is the drive, plus we can increase this even more by using some of the accelerators that we have. Now, the key message that I want to leave you with must address the customer needs. It means there's no such thing as one solution that can meet everybody's needs. So that's why we provide a high performance drive without sacrificing latency. We have a very low latency product, very low latency product, and which is important, using a TLC NAND, which means it doesn't cost a lot. And capacity. We provide very high capacity drives. And add value to your storage products. That's very important. And how do you do that? Is make your SSD smarter. It really pays off big time in application performance. Okay? Thank you. And again, Another cartoon to, to make you laugh. The presentation is available in the latest technology. The videos are available in VHS and Betamax format. So make sure you can pick up one of those tapes. Very high capacity. Okay. Thank you.